everyone, and welcome back to another chapter of our Physics O-Level lessons. This is our 7th chapter and it's called Rays and Waves. In this chapter, we're going to learn about light, wavelength and color of light, laws of reflection, how we find an image's position in a mirror, refraction of light, the refractive index, what is total internal reflection, reflecting prisms, we're going to learn about the Snell's law, what the critical angle is, lenses, and lastly the electromagnetic waves and spectrum. So let's begin with understanding light. So light is a part of the electromagnetic spectrum which is visible to our eyes. It usually travels in straight lines and it changes direction only if it hits a shiny surface or if it travels from one material to another. So this change in direction at a shiny surface such as a mirror is called reflection. So when light hits something and changes its direction, it's more like bouncing off of something, bouncing off of a shining surface. This is called reflection. So for you to see something, light must enter your eyes. So the sun, lamps, lasers and glowing TV screens all emit their own light. These things are luminous. By luminous we mean the materials that emit their own light, like lamps. They don't need any light to be reflected off of them for them to be able to be seen. They emit their own light and so they are called luminous. However, most objects are non-luminous. You see them only because daylight or other light bounces off them. So these materials reflect light. And some of this reflected light goes into our eyes, which forms our view. So non-luminous objects are the things which need light to be bounced off of them for them to be able to be seen. Most of the things like solid objects which don't emit their own light. Almost everything is non-luminous except for lamps, lasers and glowing TV screens as well as the sun. These are luminous, they emit their own light. So this was non-luminous and luminous objects and how light is necessary for us to see something. So we can only see something if light reflects from that object and goes into our eyes. So you can see a book page because it reflects light. The white parts reflect most light and look bright. However, the black letters absorb nearly all the light striking them. So they reflect very little and look dark. Well, right now you're probably looking at a screen. So unlike a book page, a screen emits its own light. You're probably watching this video on your phone or your tablet or your laptop or any other device, and this device that you're looking at emits its own light, so it is luminous. Whereas a book page is non-luminous, it needs light to be reflected off of it for it to be able to be seen. So most surfaces are uneven or contain particles that scatter light. As a result, they reflect light in all directions, which means that the reflection is diffuse. However, mirrors are smooth and shiny, so when they reflect light, the reflection is regular. This is what we mean here. So this is a mirror, as you can see, it is a smooth surface. So the reflection is regular. It is at the same angle but in the opposite direction and they are straight. And the rays are straight. But over here, we have a rough surface. And so when incident rays strike on them, the reflected rays act in all directions. So this reflection is diffuse and this reflection is regular. Transparent materials like glass and water let light pass right through them. So they transmit light. Here is transmission. Light passes through this object. So this object, this is perhaps glass, transmit lights. This object absorbs light. So the rays are absorbed by this object. And this object reflects light. So the rays bounces off of this object, and because it is smooth, the reflected rays are regular. So this is a regular reflection. So now that we've understood light, we're going to move ahead on to looking at the features of light. So here we have a couple of features of light. Let's go through them one by one. Firstly, light is a form of radiation. This means that light radiates, which means that it spreads out from its source. Of course, so the light radiates from its source, it spreads out from its source. And so in diagrams, lines called rays are used to show which way the light is going. These are the lines basically represent rays. They're also called rays. Okay, secondly, light travels in straight lines. We all know about this, of course. You can see this if you look at the path of a sunbeam or a laser beam. Even if light bends, it doesn't curve. The rays don't curve. They just change their direction. So light do not bend. They always travel in straight lines. Whether they're reflected, refracted, or diffracted, they travel in straight lines. Thirdly, light transfers energy. So yes, energy is needed to produce light. Materials gain energy when they absorb light. So for example, solar cells use the energy supplied by sunlight to generate electricity. If we stand in sunlight, we can feel the hot weather. So light transfers energy. Fourthly, light travels as waves. We read about this in the previous chapter as well, waves and sounds. So light radiates from its source rather as ripples spread across the surface of a pond. However, in the case of light, the ripples are tiny vibrating electric and magnetic forces instead of water. Light waves have wavelengths of less than 1,000th of a millimeter. So like other waves, they can be diffracted. But the effect is too small to notice unless the gaps are very narrow, for example, as in a fine mesh. Well, I can give you an example of the diffraction of light. If we close the door of our room and don't turn the light on, keep it dark, then the light from outside comes in through the keyhole of the door. And you can see that the light is diffracted from the keyhole. It spreads out if you notice it. The rays spread out. They're not like straight. They do spread out, okay? So some effects of light are best explained by thinking of light as a stream of tiny energy particles. Scientists call these particles photons. Okay, so I hope you have understood this as well. Light can travel through the empty space. This is the fifth point. Electric and magnetic ripples do not need a material to travel through. And so that is why light can reach us from the sun and stars. Even though the space is empty, it's a vacuum. There's no air in it, but still light travels us through it. So light can travel through empty space. And lastly, light is the fastest thing there is. Well, you can see this. In a vacuum, in space for example, the speed of light is 300,000 kilometers per second. And nothing can travel faster than this. So the speed of light seems to be a universal speed limit. Well, these were the 6 features of light. I hope you have understood these features of light. So we're going to move ahead on to understanding wavelength and color. So when light enters the eye, the brain senses different wavelengths as different colors. The wavelengths range from 0.0004 millimeters, which is violet light. It is a violet color, to 0.0007 millimeters, which is red light. And white light is made up of all of the wavelengths in this range. So the original color of light is white. We all know that, of course, right? So if a white object is placed, light reflects off of it and it appears white. So all of the wavelengths add up to the white light. So white light is made up of all of the wavelengths. So when they hit a white object, it appears white. If the object is blue in color, then the blue light wavelength is reflected off of it. So when light strikes the object, the wavelength of light, which appears to be blue in color, reflects off of it, and the other wavelengths get absorbed into this. And the other wavelengths, like the 0.004, which is violet light, and 0.007 red light, and more of them, like the green, yellow, and orange, they all get absorbed. But only the wavelength of the blue light gets reflected off of the blue object. In the same way, if the object is red, Only the wavelength, which is 0.007 millimeters, gets reflected off the object, and the others get absorbed into them. The white color is made up of all of these wavelengths, so all of them get reflected off of it and it appears white. And if the object is black in color, then all of the wavelengths get absorbed, so nothing gets reflected off the object and the object appears to be black. So this is how we see color. So when light enters the eye, the brain senses different wavelengths like 0.0007 millimeters as red light, so different wavelengths as different colors. Most sources emit a mixture of wavelengths. However, lasers emit light of a single wavelength and color. Light like this is called monochromatic light. You probably have seen lasers, they're like only red light, and so it is only of a single wavelength and color, which is probably 0.0007 millimeters because lasers are red in color. So a light like this is called a monochromatic light. It emits only one wavelength and color. Otherwise, most light sources emit a mixture of wavelengths. So this was all about wavelength and color. I hope you have understood it. And it's very simple to understand as well. So it means that light enters the eye and the brain senses different wavelengths as different colors. So yes, colors are made up of different wavelengths, 0.007 millimeters as red light, 0.0004 millimeters as violet light, and the wavelengths in between both of these wavelengths are other colors. We're going to learn more about colors and light in the electromagnetic topic of this chapter. But for now, we're going to move ahead onto understanding the laws of reflection. So, when a ray of light strikes a mirror, it is reflected. Here is what I'm talking about. So, a ray of light from this woman's forehead struck a mirror and it got reflected back into her eye. In the same way, we have light coming from here and gets reflected in her eye. So the incoming ray, which is this one, which is basically the ray which hits the object before it becomes reflected, this ray is called the incident ray. And the outgoing ray, which bounces off of the mirror, is the reflected ray. You can see this by the arrows. So the ray which is moving towards the mirror and is striking the mirror is the incident ray, and the ray which goes away from the mirror is the reflected ray. So the line at right angles to the mirror's surface is called a normal, which is this line, as you can see. So this is at right angles to the mirror's surface, and this line is called a normal. This line is at the center of the reflected and incident rays, as you can see here. Well, let's look at what we are talking about here. So there are two laws of reflection, and they apply to all types of mirrors, curved or plane mirrors. So the first law is that the angle of incidence is equal to the angle of reflection. So you can see this over here. This is the incident ray, and we measured the angle of this incident ray, and this is the reflected ray. The point where the ray bounces off is the point from where we are going to draw a normal out. So a normal is at right angles to the mirror's surface. It is going to be straight like this and is going to be at right angles to the mirror's surface. We're not going to change the angle of it. So make it a straight line right at the point where the ray of light strikes the mirror. So this is the incident ray, and the angle at which this incident ray is moving is called the angle of incidence. So this angle of incidence is equal to the angle of reflection. The angle of reflection is the angle of the reflected ray. So this is the angle of reflection and this is the angle of incidence. And you can see that both the angles are equal but in opposite directions. So this is the first law of reflection. The angle of incidence is equal to the angle of reflection. The second law of reflection is that the incident ray, the reflected ray, and the normal all lie in the same plane. So by this we mean, as you can see here, this is the plane. The mirror is the plane. So these rays, the normal, the reflected, and the incident ray, all of these rays lie on this same plane, which is the mirror. So the plane at which the incident ray strikes and gets reflected is the plane on which all of these rays lie. So put another way, light is reflected at the same angle as it arrives, and the two rays and the normal can all be drawn on one flat piece of paper. These were the two laws of reflection. I hope you've understood them, and they're pretty easy to understand anyways. So let's see what an image in a plane mirror looks like. In this diagram, light rays are coming from the girl in front of a plane mirror. After reflection, some of the rays enter the girl's eyes. So to the girl, they seem to come from a position behind the mirror. So that is where she sees an image of herself. So these dotted lines, as you can see, have been drawn to show the point where two of the reflected rays appear to come from. So this is the reflected ray, and it appears to come from here, and this ray appears to come from here. So to her eyes, these rays appear to be coming from a position behind the mirror. So that is how she sees her whole body in this small mirror, even though the mirror is only of this height. She can still see her legs and feet. So the image seen in the mirror looks exactly as the person, apart from one important difference. The image is laterally inverted, which means it is back to front. So this is the image in a plane mirror. It is the same as the person, but it is laterally inverted. Real and virtual images. So in a cinema, the image on the screen is called a real image because rays from the projector focus to form it. So the image in a plane mirror is not like this. Although the rays appear to come from behind the mirror, no rays actually pass through the image and it cannot be formed on a screen. So an image like this is called a virtual image. The difference between a real image and a virtual image is that a real image is formed by the actual intersection of light rays, whereas a virtual image is formed by the imaginary intersection of light rays. So a real image can be formed in a screen, but a virtual image can only be seen in a mirror. So when the intersection of light rays actually happens, a real image is formed. But if it is only an imaginary intersection of light rays, then a virtual image is formed. We might look into more details about this in the upcoming topics of this chapter as well. So this was the image in a plane mirror. Now that we've understood this, we have also understood the incident ray and the reflected ray and the normal line and the two laws of reflection. So we're going to move ahead onto now finding an image position in a mirror. So to find the actual position of the image formed in a mirror, we have seen in this that the image is formed somewhere behind the mirror. But we can't see it, of course. We just think that the image is somewhere here. So how can we find the position of the image behind the mirror? This is what we're going to find out over here. So finding an image position in the mirror. So the first step to do this is to put a mirror upright on a piece of paper. We put a pin in front of the mirror and mark the positions of the pin and the mirror on the piece of paper. Okay, then this is the view. So then if a second pin is put exactly in the same position as the image of the first pin, it should stay in line with the image wherever you view it from. So if we put a search pin at exactly the same position as the image of the first pin, which is this one, then it should stay in line with the image, which is the mirror image, wherever you view it from. So scientifically speaking, there should be no parallax. If you see it from here, it should stay on top of each other. It should stay in line. If we view it from here as well, anywhere, scientifically speaking, there should be no parallax, which means that there should be no relative movement between the second pin and the image when you change your viewing position. So this is the image of the nail and this is the real nail behind the mirror. So right now there is no parallax, but if the search pin is not put at the right position, then there is going to be a parallax and it's not going to be in line. So if there is relative movement, which means there is parallax, then the two are not in line. Mark the search pin's position as well, and we take off all of the things from the paper, and what we will see is that the image of the pin, which would be the point of the search pin, is as far behind the mirror as the object is in front. So the distance between both the pins from the line of the mirror is going to be equal. As you can see here, it is being shown that it is an equal distance. The image of the pin is as far behind the mirror as the object is in front, and the image is going to be the same size as the object. Also, a line joining equivalent points on the object and image passes through the mirror at right angles. So this is how we find an image position. Now we can also find an image position by construction, which means by diagrams. So there are two methods of finding an image position by construction. So this is the first method. In the diagram here, O is a point object in front of a plane. By plane we mean flat. In front of a flat mirror. This is the mirror. So here we have two methods of finding the position of the image by geometric construction using a protractor. So this is the method 1. In this method 1, you deduce the position from the paths of two rays. But method 2 is simpler, so we're going to see the method 2 later. Let's see the method 1 first. Firstly, from the object O, we draw a ray which strikes the mirror at an angle of incidence of 35. And then we construct a normal line at the right angles to the mirror surface. So this is the normal we're talking about. So then we construct a normal at the point where the ray strikes the mirror. This is a line at right angles to the mirror surface. Then we draw a reflected ray from this point so that the angle of reflection is equal to the angle of incidence. After this, we repeat steps 1 to 3 for a second ray with an angle of incidence of 55. Now, what we do is that after the fourth stage, we extend the two rays backwards until they intersect. Something like this, as you can see. So these are the reflected rays, and we extend them backwards behind the mirror, extend them until they intersect. So the point of intersection, which is called I, is the image position. So this is how we find an image position by construction, geometric construction. And as you can see, the image is just as far from the plane mirror as the object is at the front of the mirror. So the distance between the two is equal. Now, this was method 1. We make two lines and we extend the reflected rays backwards until they intersect, and so the point of intersection would be the image position. Now, the second method is far simpler. So this method uses the fact that the position of the image behind the mirror matches that of the object. So number 1, from the object O, we draw a line which passes through the mirror surface at right angles. Remember, at right angles. Not any angle, at right angles to the mirror, which is going to be a straight line. And we extend this line well beyond the mirror. So we measure the distance from the object to the mirror, which is going to be this distance, only this distance. We measure it from the object to the mirror. And the third step is going to be that at an equal distance behind the mirror, we mark a point on the extended line. This point is going to be I, the image position. Rather than method 1, this is far simpler because it uses the fact that the position of the image behind the mirror is just as far from the mirror as the object is in the front of the mirror. So we just measure the distance of the object from the mirror and we draw a line of this length behind the mirror and we can find the image position. These were the two methods we used to find an image position by geometric construction. So now that we've understood how we can find an image position either by construction or by the manual method, we have understood how we can do it, the three methods of finding an image position. And we have also understood the fact that the distance of the image from the mirror is going to be equal to the distance of the object from the mirror. So they're going to be equal to each other. So now that we've understood all of this, we can move ahead onto some reflection problems. That is, some questions. So here we have the first question. A horizontal ray of light strikes a plane mirror whose surface is angled at 55 to the ground. So this is the ground and this is the mirror, which is angled from the ground at 55 degrees. And this is the incident ray which strikes this plane mirror. So what is the angle between the reflected ray and the ground? So how to find the answer of this? So in this diagram, as you can see, the angles A, B and C have also been labeled to help with the calculation. So the incident ray is parallel to the ground. So the angle between the reflected ray and the ground is going to be equal to C plus B, because it's the same. So the incident ray is the same angle to the ground, so it's the same thing as the ground. Well, as the incident ray is parallel to the ground, A is going to be equal to 55 degree, because the mirror is also at 55 degree and the incident ray is parallel to the ground. Angle A is also going to be 55 degrees. But A plus B is going to be 90, as you can see here, because the normal is at right angles to the mirror, so this is making a 90 degree angle. So basically the angle of B plus A is going to be 90. So we minus the angle 55 from 90 and we will get 35. So basically from this angle we minus the 55 angle, which is this one, and we get the angle of B here. And what we get is 35 degrees. So B is going to be equal to 35 degrees. As the angle of reflection is equal to the angle of incidence, C is equal to B. C is equal to B. So C is going to be equal to 35 as well if B is 35 degrees. So therefore B plus C becomes 70. And so the angle between the reflected ray and the ground is going to be 70 degrees, because the incident ray is parallel to the ground. We take the incident ray as the ground. So the angle of the reflected ray from the ground is 70 degrees. This was such a cool question, wasn't it? And an interesting way of finding the answer. We know the angle of the incident ray because we know the angle of the mirror from the ground, and because the incident ray is parallel to the ground, the angle of A is going to be equal to the angle of the mirror, which is 55 degrees. So when we found this angle, we can see that the normal, of course, every normal line is at right angles to the mirror, to the surface it is acting on. So B plus A would be equal to 90 degrees. So when we minus the 55 degree from 90 degree, we will get 35. So we will say that the angle B is equal to 35. And so B is equal to C, so C is also going to be 35. And when we plus both 35, we get 70. And that is how we find the angle of the reflected ray from the ground, 70 degrees. Now this was one example, one question. Let's move ahead on to doing another question of the same example here. The mirror is re-angled to reflect the ray vertically upwards. Before it was something like this. But now the mirror is re-angled, so the reflected ray is vertically upwards. Now they're asking what is the new angle between the surface of the mirror and the ground. So now angle A, B, C and X all have new values. But you can still see that the incident ray is parallel to the ground. But we don't know the angle of A because we don't know the angle of the mirror. As before, as you can see here, that A plus B is equal to 90. And so C is equal to B. And X is the unknown angle between the surface of the mirror and the ground. So X is the unknown angle between the surface of the mirror and the ground. So X is equal to A. As the reflected ray is vertically upwards, B plus C would be equal to 90. So here we have it. If we half 90, we can see that C and B are both 45 degrees, because the reflected ray and the incident ray, this is a 90-degree angle. So if we half the 90, we get 45. So C and B are both 45 degrees. Are both at 45 degrees, so B and C. So now what we know is that because B is 45 degrees, B plus A is equal to 90 degrees. You can also see that here, which means that A is also equal to 45 degrees because it is also at 90 degrees. So B is 45, then A is also 45. So if B is 45, A is also 45. So therefore, the angle X is also 45 degrees. So the angle between the surface of the mirror and the ground must be changed to 45 degrees. So all of the angles over here are at 45 degrees. So it's such an interesting way you can find this out, because we know that reflected ray and incident ray are at 90 degrees, and the angle A and the angle B are also at 90 degrees, because the normal is always at right angles to the mirror surface. We cannot find this out by here. We cannot say that the incident ray, that this ray is at the center of the angles B and A. But we do know that the normal is always, it must be at right angles to the mirror surface. So because the reflected ray and incident ray are at 90 degrees, we can say that the angle C and angle B are both 45 degrees. And because B is 45 degrees and B plus A becomes 90 degrees, so A is also going to be 45. And that is how we find the angle X, which should be equal to A as well. So it is going to be 45 as well. So this was the second question of the same example. So I hope you have understood the reflection and how we find the image position, the image in a plane mirror, the laws of reflection. So now that we've understood reflection and we've also done some questions related to reflection, we are going to move now towards refraction. So refraction, the word refraction, so let me tell you this, the word refraction means fractured. First, let's understand what refraction is. So here you can see the broken stick illusion. This illusion occurs because light is bent by the water in the glass. So this bending effect is called refraction. So it feels like the stick is broken. The word refraction is related to the word fractured, which means broken. So here is what we're talking about. This diagram shows how a ray of light passes through a glass block. So the line at right angles to the side of block is called a normal. These are the normals. So the ray is refracted towards the normal when it enters the block and away from the normal when it leaves it. The ray emerges parallel to its original direction provided the block has parallel sides. So refraction occurs when this ray from this ray box is passing through a glass block. So we've understood this before, that a change of material causes the light rays to bend. So a glass block is a denser medium than the outside of the block. So when the incident ray goes into the block, it bends towards the normal because it went into a denser medium than air. But if the light ray had passed from a denser material to a less dense material, as you can see here, it will go away from the normal, which is the case over here. The glass block is denser than the air outside, so when it leaves it, it goes away from the normal. So this is what refraction is. A change of material causes bending. We've also read this, that light always travels in straight lines, so whenever it bends as well, it only bends at the point it enters a different material. So it basically changes directions rather than bending. So it's not like it becomes curved or anything, it just changes its direction like this. But the beam always remains straight. So refraction would also occur if the glass weren't replaced with another transparent material such as water or acrylic plastic, although the angle of refraction would be slightly different. So anything can be replaced by this glass block, but refraction would still occur because the medium is different from the medium here. So whether it's a glass block, a plastic block, or anything, the light would still bend because the medium is going to be different from the medium outside, from air. So that is why refraction occurs. A change of medium, a change of material causes light to bend. But it comes back to its original angle when it gets outside of the glass block. As you can see, the angle of incidence and the angle of reflection are equal, but they're not equal if it is inside the glass block because it is a different material. A denser material would cause the light ray to go towards the normal, and a less dense material would cause the light ray to go away from the normal. So this is refraction of light. I hope you have understood it. This is also the same thing that happens to this stick. It gives a broken stick effect. Well, this can be explained over here by real and apparent depth. What do we mean by this? So because of refraction, water or glass looks less deep than it really is. So we see an apparent depth. Its apparent depth is less than its real depth. So sometimes when we see through the water, we see a fish over here. We think that the fish is at this level, whereas the fish actually is at this level. So the apparent depth, we see the apparent depth, of course, we don't see the real depth. So the apparent depth is less than its real depth. What happens is that the light from this fish gets refracted when it comes outside of the water. So if we extend this angle, rather than this angle, we extend it over here. So we see that the fish is over here. We think that the fish is over here because the light is refracted and we see the apparent depth of the fish. This is the apparent depth and this is the real depth. dA, depth apparent, dr, depth real. So that is how we think that the fish is at this level rather than this, because the light rays from this fish get refracted from here. Basically what happens when light rays enter any other block, when they are outside in air, the light waves have a higher speed, so their wavelength is big. But when they enter the glass, their speed becomes less because it is denser than the air outside, and the wavelength increases, which causes the light to travel at a slow speed. This is what happens in refraction. Now let's see why light is refracted. Why light is reflected? Light is made up of tiny waves, and these waves travel more slowly in glass or in water than in air. So when a light beam passes from air into glass, one side of the beam is slowed before the other, and this makes the beam bend. Remember, if the angle of incidence of the ray is right angles to the glass block's surface, then there will be no bending, because this thing won't happen, that one side of the beam is slowed down before the other. There won't be any side which comes first or later. They will come at the same time together, and so that will cause no bending. But if the incident ray is not at right angles to the surface of the glass block, then one side of the rays enter the glass block first and they slow down before the other side. And so one side of the beam is slowed down before the other, and this makes the beam bend towards the normal. In the same way, when they leave the glass block, this side of the ray is fastened up before this side, and this makes the beam bend in this direction. So this is how light is refracted. I hope you've understood this. It's pretty simple, right? That when the light beam passes from air into glass, one side of the beam is slowed down before the other side, and this makes the beam bend. This is how light refracts, and the refraction causes us to see an apparent depth rather than the real depth, because the light gets refracted when it leaves the water surface. So its apparent depth is less than its real depth. So now that we've understood refraction, we're going to look at the refractive index. What is a refractive index? So, in a vacuum, the speed of light is 300,000 kilometers per second. This is the speed of light, and in air, it is effectively the same. However, in glass, the light slows down to 200,000 kilometers per second. So the refractive index of a medium is defined like this. The refractive index of a medium, it is of a medium. So the refractive index is equal to speed of light in vacuum divided by the speed of light in the medium. Whatever the medium is, then we will find the refractive index of that particular medium. So in this case of glass, the refractive index would be equal to the speed of light, which is 300,000 kilometers per second, divided by the speed of light in glass, which is 200,000 kilometers per second. And we will get 1.5. So here we have some refractive index value. The medium with the highest refractive index has the greatest bending effect on light because it slows the light the most. So diamond has the greatest refractive index, as you can see, which means the diamond bends the light most. In other words, it slows it down. Then we have glass. After diamond we have glass, and then we have acrylic plastic, and lastly we have water, which has the least refractive index. These figures are based on more accurate values of the speed of light than these used here in this. This is how you find the refractive index of a material. The refractive index is basically how much a medium bends light or slows it down. So the medium with the highest refractive index has the greatest bending effect on light. So the medium with the highest refractive index has the greatest bending effect on light as it slows the light the most. So this is what refractive index is. Now that we've understood this and the equation of the refractive index, we're going to move ahead on to understanding the refraction by a prism. In other words, we're going to look at the dispersion of light. So white light is split up into a spectrum through a prism. A prism is a triangular block of glass or plastic. The sides of a prism are not parallel, so when light is refracted by a prism, it comes out in different direction. So light is deviated when it gets refracted by a prism and comes out in different directions. If a narrow beam of white light is passed through a prism, it splits into a range of colors called a spectrum, like this. The effect is called dispersion. The dispersion of light occurs because white is not a single color, but a mixture of all the colors of the rainbow. So the prism refracts each color by a different amount. So here, as you can see, this white beam of light enters the prism and gets refracted into a spectrum of light. All of the colors of the spectrum are the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. So this is the dispersion of light. Now let's look at the total internal reflection. So the inside surface of water, glass, or any other transparent material can act like a perfect mirror, depending on the angle at which the light strikes it. So here we have the diagrams which show what happens to three rays leaving an underwater lamp at different angles. So there's a lamp underwater, and here we have three different diagrams of the rays leaving this lamp. Each diagram shows the rays leaving at a different angle. So here, as you can see, the light gets refracted when it leaves. But there is also a weak reflection of light which comes back into the water. The light bounces off the water surface and gets reflected. So while it is being refracted, it is also being reflected. In this diagram, as you can see, we have an angle which is denoted as C. So this angle C is called a critical angle, where the refracted ray is parallel to the water surface. For any angles of incidence greater than this, there is no refracted ray. All the light gets reflected. And so this effect is called total internal reflection. Like here, this angle is greater than the critical angle, which is this one. So there is no refracted ray, only reflected rays. This is called total internal reflection. The critical angle is when the refracted ray is parallel to the surface of water. So any angles of incidence greater than this, there is no refracted ray. All the light gets reflected, and the result is total internal reflection. So the value of the critical angle depends on the material. For example, water has a critical angle of 49 degrees, whereas acrylic plastic has a critical angle of 42 degrees. So each material has a different critical angle. Glass has 41 degrees and diamond has 24 degrees. So these are some critical angles you can memorize. So we can also see how total internal reflection occurs in prisms, reflecting prisms. So the inside faces of prisms are being used as mirrors in these cases. Total internal reflection occurs because the angle of incidence on the face is greater than the critical angle for glass or perspex. So as you can see, this is a periscope. A periscope is an instrument for looking over obstacles, like over water. Like submarines and marines use periscopes to see over water, even though they're underwater. So prisms reflect the light, although they can be replaced with mirrors. Like in this example, we are showing mirrors, but instead of these, we can also put prisms. So light rays from the source, like from the outside, enters the periscope, and the prism or the mirror reflects the light downwards like this. And here we have another mirror or prism, whatever you want, and it gets reflected towards this place, which is the eyepiece. So from here we see above the water. This is how the rays come from the top to the bottom. So using mirrors or prisms, light gets total internally reflected like this. So this is one example, the periscope. We have another example, which is the binoculars. So the lens system in each barrel, this is just a single barrel we're showing here. The same is over this side, the opposite side. So the lens system in each barrel produces an upside down image. So that is why reflecting prisms are used to turn it the right way up. Light rays enter the binoculars from here and gets total internally reflected by this prism, goes towards this prism and gets reflected, and the light rays come out from here. This is the eyepiece. So this is how we use prisms for total internal reflection in different instruments like the periscope and the binoculars. There are many more, but these are the two examples. Now another example of total internal reflection are optical fibers. So optical fibers, these are very thin flexible rods made of special glass or transparent plastic. So light put in at one end is total internally reflected until it comes out of the other end. Although some light is absorbed by the fiber, it comes out almost as bright as it goes in, even if the fiber is several kilometers long. You may have seen optical fibers in cables and wires. When you cut open a wire, we can see bundles of optical fibers. An optical fiber is very thin and is made up of special glass or transparent plastic, and they are flexible. So a bundle of optical fibers, provided the fibers are in the same positions at both ends. So optical fibers can carry telephone calls and internet data. The signals are coded and sent along the fiber as pulses of laser light. Fewer booster stations are needed than with electrical cables. So this is what an optical fiber looks like. These are optical fibers, and as you can see, there is light coming out of these optical fibers, which is total internally reflected. These are bundles of optical fibers. Also, provided the fibers are in the same positions at both ends, a picture can be seen through them because of these light rays being total internally reflected. So here you can see in detail, a single optical fiber is coated with plastic, and then the bundle of these optical fibers is put in this plastic and it makes a cable. So electrical cables contain these optical fibers, these colorful wires in which there are these optical fibers which have light total internally reflected from one end coming to the other end. Optical fibers are also used in endoscopes. An endoscope is an instrument used by surgeons for looking inside the body. An endoscope contains a long, thin bundle of optical fibers. So endoscopes can be used to take photographs to see inside the body. So this was total internal reflection and the different examples of internal reflection. The optical fibers are one, reflecting prisms, and how we use that in different instruments like the binoculars and the periscope. Prisms are used for total internal reflection. And what total internal reflection is actually. So I hope this is all clear to you now, that if you've understood the critical angle, the total internal reflection, and refraction. Memorizing these critical angles of different materials can be helpful. So now we're going to move ahead onto understanding the Snell's law. So, when light is refracted, an increase in the angle of incidence produces an increase in the angle of refraction. Remember, the sign of incidence is I, and the sign of angle of refraction is R, small I and small r. So, in 1620, the Dutch scientist Willy Brood Snell discovered the link between the two angles. The link was that their signs are always in proportion. So when light passes from one medium into another, this is what happens. Sin I, which is the angle of incidence, divided by sin R, which is the angle of refraction, equals to n. N represents the refractive index. And this is known as Snell's law. This equation leads us back to the refractive index equation, which was the refractive index is equal to speed of light in vacuum divided by speed of light in medium. So in a vacuum, the speed of light is 300,000 kilometers per second and effectively the same in air. But in glass, it drops to 200,000 kilometers per second. We have read this, of course. So the refractive index of glass is 300,000 kilometers per second divided by 200,000 kilometers per second, which is 1.5. So this is the same as the value of sin I divided by sin R. So there are two ways we can find the refractive index of a medium. Firstly, we can find the refractive index by dividing the speed of light in the vacuum and the speed of light in the medium of which we are finding the refractive index. So when we divide both the values, we will get one. Then we have the refractive index equation, which is the Snell's law. This equation is sin I divided by sin R. And this is used only when we know the angle of incidence and the angle of refraction. So this is a different equation compared to this equation. So like in this question, we are given the angle of incidence and the refractive index of water. So finding the angle of refraction is pretty simple. All we have to do is rearrange the equation and substitute the values. First we substitute the values. Sine 45 degrees divided by sine r is equal to 1.33. We rearrange this equation. How do we rearrange this equation? It is simple. We use the triangle method again. We put the sine I above and refractive index and sine r multiplying together below. This is how we make the triangle. Remember, if we're given the equation like this, then the value which is being divided by something and then it equals to something, that value which is at the top will remain at the top and the other values will go below it. Or if the equation is given like this, that two values are being multiplied together, like force is equal to ma is an equation. So we read it as F is equal to ma. So we see that m is being multiplied by a and we get F. So there are only two values that are being multiplied. And these values go at the bottom. And so F goes on the top. So any value which is being divided will remain on the top and the other values will come down to it, so that rearranging the equation is simpler. So then what we will get is sine I divided by refractive index multiplied by sine R. This is the triangle method. So in this case we want to find the sine R, the angle of refraction. So we will hide the angle of refraction and what we will get is sine I divided by refractive index. So we're not multiplying them, we're dividing them. The values which get multiplied are the refractive index and the sine R to get sine I. So to get the angle of refraction, we divide 45 degrees by 1.33 and when calculated, this gives sine R 0.532. So the angle of refraction is 32 degrees. After rounding off, the angle of refraction is 32 degrees. So this is the Snell's law equation. N represents the refractive index, sine I represents the angle of incidence, and sine R represents the angle of refraction. So Snell's law is basically that the sines, sine I and sine R, are always in proportion, which means that when they are divided together, we get the refractive index. So this is Snell's law, that sine I and sine R are always in proportion. Okay, so now that we've understood Snell's law and the equation, we're going to look at how we can calculate the critical angle. So we have these diagrams back in, and in these diagrams you can see that rays are traveling from glass towards air at different angles. This is glass, even though there's water written, but let's assume that this material is glass and this material is air. So the rays are traveling from glass towards the air at different angles. But when the angle of incidence is greater than the critical angle, then there is no refracted ray. All the light is reflected. This is total internal reflection. So knowing the refractive index of a material, the critical angle can be calculated. Let's see the middle diagram here. This is the critical angle. But this diagram has been redrawn with the ray direction reversed. This time, the angle of incidence is 90 degrees and the angle C, which is the critical angle, is now the angle of refraction. So, if the refractive index of glass is 1.5, sine C is equal to 1 divided by n. 1 divided by the refractive index, and we will get the critical angle. The refractive index will be equal to sine 90 divided by sine C, which is the critical angle. And what we will get is 1 divided by sine C to get the refractive index. This is what happens if we rearrange this equation. So then, rearranging the equation, we'll get sine C is equal to 1 divided by the refractive index, 1.5. And we will get 0.67. So 1 basically represents sine I, the angle of incidence, which is 90. But we won't write 90, we will call it 1. So we will divide 1 by the refractive index to get the critical angle. And what we get is 0.67. So C, the critical angle of glass, is equal to 42 degrees. Okay, remember, this figure differs slightly from this spread, as you can see, because a simplified value for the refractive index of glass has been used in this calculation. The refractive index of glass is 41 in actual, but here we are using a simplified value. From this calculation, it follows that the critical angle of any medium can be calculated using this equation, which is sine C is equal to 1 divided by n, the refractive index. So for a medium of refractive index n, we can divide 1 by n and we will get sine C, which is the critical angle. So I hope you have understood how we can calculate the critical angle. And now we've understood the refractive index equation, sine I divided by sine R, Snell's law, the equation of Snell's law, sine I divided by sine R is equal to n. Optical fibers, prisms, reflecting prisms, critical angle, total internal reflection and critical angle, and the dispersion of light. So we're going to move ahead now onto another topic of this chapter, which is lenses. Now this is going to be very interesting. So lenses basically refract light to form images. Now we're going to look at the two main types of lenses. These are the convex lenses and the concave lenses. So these are the convex lenses. The convex lenses are also known as the converging lenses. Convex lenses are thickest in the middle and thin around the edge, as you can see here. So when the rays parallel to the principal axis pass through a convex lens, the principal axis is a line going through the lens from the center of the lens, and they are at right angles to the lens. So when rays parallel to the principal axis pass through a convex lens, they are bent inwards. So basically the rays are converged by a convex lens. That is why it's called a converging lens. So the point where they converge, which means the point where all the rays meet, is called the principal focus. So its distance, the principal focus's distance from the center of the lens, is known as the focal length. So here's what we're talking about. This is the convex lens, this is the concave lens. Let's look at this one right now. So as you can see here, the rays are parallel to the principal axis. The principal axis is a straight line like this one here. And they are parallel to the principal axis, but when they pass through a convex lens, they converge like this. And they meet at one point. All of the rays meet at this point, so this point is called the focal point. And the distance of the focal point from the convex lens, the center of the lens, is the focal length. So this type of convex lens is known as a converging lens as well. So rays can pass through the lens in either direction, from here or from here. So there is another principal focus on the opposite side of the lens and the same distance from it. This is the focal point over here somewhere. So the distance, the focal length of this focal point is equal to the focal length of this focal point, because rays can pass from either direction, either from here or from here. It doesn't matter. So that is why we have two focal points here at equal distances from the convex lens. So this was the convex lens, the converging lenses. Then we have the second type of lens, which is the concave lens. These are the diverging lens. So these lenses are thin in the middle and thickest around the edge. So when rays parallel to the principal axis pass through a concave lens, they are bent outwards. So they are diverged, in other words. Convex lens bring rays together, whereas concave lens bend them outwards. They spread out. The rays appear to spread out. So the principal focus is the point from which the rays appear to diverge, spread out. So here we have the concave lens. So these are the parallel rays. When they pass through a concave lens, they get diverged. They spread out like this. And so this is the focal point. So basically how we find the focal point is like, we find the focal point where the rays appear to come from. So these are the rays, these are the actual rays, and when they pass through a concave lens, they bend like this. But if we extend these rays with their own direction like this, all of these rays, they appear to converge at some point behind the lens, even though they're not actually converging, but we can assume they are converging. So this point where all of these rays converge in their directions, this point is called the focal point. And both the focal points behind the lens and in front of the lens are at equal distances. So when we find this focal point, we can measure the focal length of this focal point, and the same focal length would be in the front of the lens. So the focal point are at equal distances to each other. So this is how we find the focal point of a concave lens. The diverged rays, we extend them from behind like this. even though the rays are not like this, they appear to come from a point here. So when we do so, we find the focal point, a point where the rays appear to converge. So a concave lens is a diverging lens. So this was the concave lens and the convex lenses. So I hope you have understood. Convex lenses are converging lenses. They make the rays converge, and the point where they converge is called the focal point. The distance of the focal point from the lens is the focal length. So convex lens is a converging lens, whereas a concave lens is a diverging lens. It makes the rays spread out like this. And the focal point of this lens can be found if we extend these rays behind. So the point where these rays appear to converge and from there spread out, that is the focal point. So the focal point is also at the back of the concave lens and as well as in the front of the concave lens. But the distance is equal. So the focal length will be the same, either it is in front or at the back of the lens in both the lenses. So we have two focal points because the rays can come from either side, either from here or from here. It doesn't matter, so that is why we have two focal points. So these were the concave lens and the convex lens. They're pretty simple and easy to understand. Convex lenses are thick from the center and thin around the edges, whereas concave lenses are thin in the center and thickest around the edges. So now let's look at how real images are formed by convex lenses. In this diagram, as you can see, rays from a very distant object, this is the object, are being brought to focus by a convex lens. So rays come from all points on the object. It's not only this point, they come from here as well and from here as well. So we're just showing one point at the moment. There are many rays coming from all the points of this object. So take this point for example. The rays come from this point and the convex lens converges these rays at the other side, and together these rays form an upside down image. So you can see the rays came from this point, which is the top of the object, and when they are formed over here, they become the bottom of the object. So you can see that these rays form an upside down image. And so this upside down image can be picked up on a screen. So this type of image, an image like this, is called a real image. And it is formed in the focal plane. So rays from a point on a very distant object are effectively parallel. So they're not diverging or converging, they're parallel to the principal axis because they're very distant from the lens. So the image passes through the principal focus. But however, for an object at any other distance, the image is in a different position. Firstly, let's understand what real images and virtual images are. So, the differences between real images and virtual images. We call such images real images because they are produced when rays from a lens actually meet at some point to form it. Whenever rays actually converge at a point to form an image, that image is a real image. And the properties of real images are that they are upside down and can also be picked up on a screen. Okay, so this was the real image. Real images are formed when rays actually converge to form them. Whereas virtual images, basically when rays, like from a concave lens can never form a real image because they diverge the rays. Here as you can see, they can never converge. These rays never meet together to form an image. So that is why concave lenses always form virtual images, whereas convex lenses do form real images. So the rays that do not converge and form an image, that type of image is called a virtual image. So a virtual image is different from a real image. So the properties of virtual images are that they're not inverted or upside down, they're upright, and they cannot be picked up on a screen. So virtual images have these properties. Now, convex lenses can form both real images as well as virtual images. We're going to see how they form a virtual image, but for now we can see that they are forming a real image here. That's how we saw here how a convex lens forms a real image. But they can also form virtual images. We're going to see that later on. But the point to remember here is that convex lenses can form both real and virtual images, whereas concave lenses can only form virtual images. That is because the rays never converge at some point to form a real image. So for a real image to be formed, rays have to be converged. So concave lenses cannot form real images. So this was the real image and the virtual image. I hope you have understood this here and how a convex lens forms a real image. So the rays have been shown coming from one point of the tree here, and that is the point which is being formed over here as well. It's just the difference is that it's upside down. So in the same way, rays from different points of this object, like this point and many other, are formed like this, and the image formed by the convex lens is always upside down, which means that the convex lens is producing a real image. It is formed in the focal plane, and this real image can be picked up on a screen. So this was real images and virtual images. Now, rays from a point on a very distant object are effectively parallel, so the image passes through the principal focus. However, for an object at any other distance, the image is in a different position. So we can predict where a convex lens will form an image by drawing a ray diagram. So these are the ray diagrams, just for demonstration I'm showing. These are ray diagrams. We can draw ray diagrams to predict where the convex lens forms an image. What is the position of the image? What is the size of the image? For simplicity, rays are drawn from just one point on the object. Like here, there are many points of this object, but we are showing the rays coming from only one point. So we're doing this just for simplicity. Otherwise, if we just make rays coming from all the points of the object, it will be very confusing. There will be like too many rays here to understand. So for simplicity, rays are drawn from just one point on the object. Secondly, the rays used are the standard rays. So the standard rays, these are chosen because it is easy to work out where they go. So these are the standard rays. These are the three rays we use to make a ray diagram. But remember, only a pair of these rays can be used. Not all three are used. Only two of these rays are used to form a ray diagram. Either there can be like many pairs. It can be like these two, these two, these two. So any two of these following rays are needed to fix the image position and size. So for simplicity, rays are shown bending at the line through the middle of the lens. But in reality, bending takes place at each surface. So the lens, this is a convex lens, okay? So there's a line coming through the middle of the lens. This is a vertical line. So this ray is not bending at all, it's a straight ray. But in this case and in this case, the ray is shown bending at the line through the middle of the lens. Whereas in reality, it takes place at each surface. But for simplicity, for ray diagrams, we show it bending from here. Okay. So these are the standard rays. Let's look at each of these rays to understand what they are. So this is the first ray. So in this standard ray, rays parallel to the principal axis. This is the principal axis, so they are parallel at right angles to the lens. At right angles to the center line of the lens, as you can see. So rays parallel to the principal axis are refracted such that they pass through the principal focus. So the principal focus is at either side of the lens. So this type of ray, at first behind the lens, when it is coming towards the lens, is parallel to the principal axis, and when it is refracted that it passes through the principal focus like this. So here we can see the direction and the angle of this lens. So when it passes through the principal focus, it doesn't bend or anything, it remains straight. But this is the first ray. This ray is refracted such that it passes through the principal focus. The second ray is like this. Rays passing through the optical center pass through the lens in a perfect straight line. So optical center is the center of the lens. Point where the line through the middle of the lens is converging with the principal axis is the center of the lens. You can see this here. So in this standard ray, rays pass through the optical center of the lens in a perfect straight line like this. So this is another standard ray. The last standard ray here, as you can see, is like this. So rays passing through the principal focus behind the lens and are refracted such that they emerge parallel to the principal axis. So it's kind of like the opposite of this. It already passes through the principal focus, and after refraction it emerges parallel to the principal axis. Whereas in this one it is already parallel to the principal axis and is refracted such that it passes through the principal focus. So these were the three standard rays. We use any or two of these rays to find the image position and size, basically to form a ray diagram. So here you can see the ray diagrams. In both of these diagrams, we use these two types of standard rays. These two standard rays, this one and this one. So you can see the first ray is parallel to the principal axis, and when it passes through the lens, it passes such that it passes through the focal point of the lens. And then we extend the ray, and the other ray passes through the center point of the convex lens in a perfect straight line, and we extend this ray from the object till it converges and meets with the other standard ray. So that point where the two rays meet is the point where the image is formed. The top of the image is being formed at the bottom of the screen, which means that the image being formed is upside down, so it is a real image. And it is a real image because it is being picked up on a screen here. So these were the standard rays and how we form a ray diagram. But here I want you to see something, understand something. These ray diagrams here show that as the object is moved towards the lens, the image becomes bigger and further away. So here the object was at this point, it's like away from the lens, and this is the image being formed. But when the object came closer to the lens, the image became further away from the lens and became bigger. You can see here, so it's like the upside down distance is bigger now. Over here it was small, so it is bigger than the object over here. So basically, for example, a film projector uses a convex lens to form a magnified real image on a screen a long way from it. So basically what we're saying here is when the object is placed close to a convex lens, it forms a magnified real image a long way from it. So film projector is an example of this type of, because the reels are placed close to the convex lens in a film projector. So that is why the convex lens forms a magnified real image on a screen a long way from it. You can see that it is formed on a screen. That is how the movie is played. So this basically tells us that the closer we put the object to the convex lens, the further away and the bigger the image it forms. So speaking of magnifying, let's look at how we use a convex lens as a magnifying glass. So this is the convex lens and this is the principal focus of the lens. And as you can see, this is the position of the object from the lens. So you can see that the object is closer to the convex lens than the principal focus. So if an object is closer to the convex lens than the principal focus of the lens, the rays never converge. Instead, they appear to come from a position behind the lens. So you can see that the object, we use the two standard rays over here. So the object is closer to the lens than the principal focus. So we use this standard ray, and the standard ray is parallel to the principal axis at first, but after refraction from the convex lens, it passes through the principal focus. It is bent such that it passes through the principal focus. So it is extended then like this. And this other ray passes through the center of the convex lens in a straight line, in a perfect straight line. So then we do this, but you can see that these rays are not converging. This ray we extended further. It will never converge with the other ray. Instead, these rays appear to be coming from a position behind the lens. And these rays appear to come from this object, even though the object is somewhere here. In this case, when the object is closer to the convex lens than the principal focus, the rays never converge. And so, because the rays never converge, the image produced is a virtual image. Because of course, real images are only formed if the rays converge. So this is, like I said, convex lenses produce both the virtual images as well as real images. So a convex lens produces virtual images if the object is closer to this lens than the principal focus. Otherwise, in all the other examples we saw were showing the focal point closer to the lens than the object. That is why the lens used to always form a real image, which is upside down and can be picked up on a screen. But in this case, the image is upright and magnified, and it is called a virtual image. So if the object is closer to the convex lens, the image produced would be magnified, and it would be called a virtual image. So it cannot be picked up on a screen. So used like this, a convex lens is often called a magnifying glass. So yes, convex lens can form a magnified real image as well. But this is not how we use a magnifying glass. A magnifying glass never produces a real image, it is always a virtual image. But in the case of a film projector, the convex lens forms an image which is magnified, real, and is formed on a screen a long way from it. But still, in this case, even though the image is magnified, it is still a real image because the focal point of the lens is closer to the lens than the object. The object is not in front of the focal point, it is always at the back of the focal point of the lens. But in magnifying glass, the object is closer to the lens than the principal focus, than the focal point of the lens, and in that case, the image produced is magnified, is upright, and is a virtual image. So, stood convex lens forming virtual images and real images, and how ray diagrams are formed using standard rays. We've also understood the standard rays. We are going to move ahead on to drawing accurate ray diagrams. So how we draw ray diagrams. Of course, we know how to draw these diagrams using the standard rays. I've told this already. But if we are given a question like this, then how are we going to draw accurate ray diagrams? So in this question, we are given the measurements of an object from a convex lens. An object 2 cm high stands on the principal axis at a distance of 9 cm from a convex lens. So here we have the position of the object from the lens. The object is at a distance of 9 cm from the lens. So the distance of the object from the lens is 9 cm. We measure it out, and the height of the object from the principal axis is 2 cm. So we mark the position of the object. Okay, so remember, this diagram here is not measured accurately with these measurements. This diagram here, I've just put this diagram here for demonstration. In actual, when you make this the ray diagram, it's going to be quite different from this diagram shown over here. So, we mark the position of the convex lens. Now, if the focal length of the lens is 6 cm, what is the image's position, height, and type? So here we got the focal point of the lens. The focal point of the lens is 6 cm. So, after marking all these points, one thing is clear here. What is it? The image type is going to be real, because the object is at a greater distance from the lens than the focal point of the lens. It is behind the focal point of the lens, so the image this convex lens is going to form is going to be real. So, we are being asked what is the position, height, and type of the image. We have found the type, it is going to be real. And now we're going to find the position and height using the standard rays. So we make the first standard ray, which is rays parallel to the principal axis, refracting such that they pass through the principal focus of the lens. We extend this ray further, and then we make the other standard ray, which is the rays passing through the optical center of the lens. We extend this ray as well till it meets the other standard ray, and the point where both of them converge is going to be the image position. So we measure this point's height from the principal axis and the length from the convex lens. And what we get is that this image is 4 centimeters high and 18 centimeters from the lens. So this is how we make this ray diagram. We found the position 18 centimeter, height 4 centimeter, and type rear. It is an upside down image as well. So this is how we draw ray diagrams. Now for accuracy, you need to choose a scale that makes the ray diagram as large as possible. So when you're making a ray diagram, you might want to have 4 centimeters representing 2 centimeters so that the ray diagram is big in size. So when you make big ray diagrams, it is going to be accurate. So basically what we do is we double these values here. 9 is going to be 18 and the double of 2 is going to be 4. So we make the object 4 centimeters from the principal axis and 18 centimeters from the convex lens. So the answers we're going to get are going to be different but more accurate. But here what I have done is I have made this drawing as small as possible. So I have taken 1 centimeter representing 2 centimeters of actual distance. In simple words, I have halved the values given in this example to make a small ray diagram. That is why my ray diagram might not be as accurate as yours would be, because yours is going to be bigger in size. So what I have done is I've converted 2 centimeters into 1. So the object's height has become 1 centimeter, and the distance of this object from the lens has become 4.5 centimeters. Half of 9 centimeters in simple words. And so the answer I got was 2 centimeters high and 9 centimeters from the lens. So when I scaled up the final measurements, which means when I doubled them up, they show that the image is 18 centimeters from the lens and 4 centimeters high. So what I'm saying is that in this diagram, I have halved the values. But you need to choose a scale that makes the diagram as large as possible so that your ray diagram is accurate. So this is how we draw accurate ray diagrams. I hope you have understood this. It's pretty simple, right? We use the standard rays. The standard rays help to make these diagrams simple and easy. Okay, now estimating the focal length of a convex lens. So you can find the approximate value for the focal length of a convex lens by forming an image of a distant window on a screen or any other distant bright object. So rays from the window are almost parallel. So the image is close to the principal focus of the lens. Therefore, the distance from the image to the lens is approximately the same as the focal length. So this is how we estimate the focal length of a convex lens. It's just as simple as I just described it. So because the window is distant, the rays from the window are almost parallel to the principal axis. So the image is close to the principal focus of the lens. And so therefore, the distance from the image to the lens is approximately the same as the focal length. Alright, now let's move ahead on to looking at convex lenses in a telescope. This is another example of convex lens. So a telescope. A telescope uses 2 convex lenses. The objective forms a real image of a distant object, in this case the moon. So we're looking at the moon from a window. So the objective forms a real image of a distant object, which is the moon, just inside the principal focus of the eyepiece. So the image acts as a close object to the lens, which forms a magnified virtual image of it. So because the image is close to the object, the virtual image is going to be magnified. You've seen that, right? So the eyepiece is being used as a magnifying glass, but it is magnifying an image of the object rather than the object itself. So the final image is upside down. Most binoculars, which is basically 2 telescopes side by side, have prisms in them to turn the image the right way up. We just saw it before when we were understanding total internal reflection. So this is how a telescope uses convex lenses to magnify an image and form a virtual image. Okay, So we have understood the convex lens pretty well now. We've also learned how we can draw an accurate ray diagram of a convex lens, how the convex lens is used as magnifying glass, and how we estimate the focal length of a convex lens. So we're going to move ahead now on to looking at images formed by a concave lens. Here in this diagram you can see two standard rays have been used to show how a concave lens forms an image. And of course these standard rays are the same as I showed before, but you can see that this standard ray is not like this one here. But it is the same because in a convex lens, the lens converges these rays. So this is the shape of the standard ray, whereas in a concave lens, the rays are diverged. So the rays are going to spread out. They're not going to converge, not going to come closer to the principal axis. So that is why the shape of this ray is different from the shape of the ray with the convex lens. So we use this standard ray which is parallel to the principal axis, and after passing through the lens it is refracted such that it passes through the principal focus of the lens. But how would we see whether it passes through the principal focus or not? Because it is not coming towards the principal axis and it's not going to pass through the principal axis after refraction. So because it is going to diverge, it's going to go away and spread out. The principal focus is only at the principal axis. So to see whether it is passing through the principal focus or not, we extend this diverged ray backwards. We extend it backwards till it passes through the principal axis, and if it passes through the principal focus, the standard ray is made correct. So we basically make the ray from behind, even though this geometric construction is only apparent, it's not happening in real life, but this is the way we see whether this standard ray is passing through the principal focus or not. Because we cannot see it in the front of the lens because the ray is diverged, so it's not going to pass through the principal focus, but it does pass through the principal focus when we extend the ray behind. So this is the principal focus and this extended ray is passing through the principal focus, which means that the standard ray is drawn correct. The second standard ray is the one which passes through the optical center of the lens. The optical center is this point. So it passes to the optical center in a perfect straight line. This is how we make the diagram of concave lens. Use the standard rays to form the ray diagram of a concave lens. So wherever the object is positioned, right now it is positioned over here, the image is always small and upright. So you can see that when the rays pass through the concave lens, the rays are diverged. They are spread out rather than converged. So wherever the object is positioned, whether it's close to the lens or further away from the lens, the image that is formed is going to be always small, upright and virtual. So a convex lens is different from a concave lens. When a convex lens forms a virtual image, the virtual image is always magnified because it only forms when the distance of the object from the lens is less than the focal length and the focal distance. Because of that, the rays from the object never converge, and that is how a virtual image is formed. So when the rays do not converge, there is no real image. There is only a virtual image, and a virtual image is always upright, but it is magnified. In a convex lens, the image is magnified. And if the object is placed away from the focal point, so the distance of the object from the lens is more than the focal length, then the rays would converge at some point and a real image would be formed, which would be upside down, and it would not be magnified or not be small. It would be the exact same size as the original object size. Whereas in a concave lens, it is always small. So now you certainly have understood the difference between concave and convex lenses and real and virtual images. So now that we've understood concave lenses as well as convex lenses, we can move ahead on to looking at some real-life examples where lenses are used. And the first example is going to be the camera. So yes, the camera uses a lens to form images. A camera uses a convex lens to form a small inverted real image on a sensor at the back. So it's a real image because the rays actually meet at some point to form the image, and the image is upside down. So as you can see, the rays from different points of this buoy refract from this lens and converge to form a real image on a sensor at the back of the camera. The image sensor is a light-sensitive microchip containing millions of microscopic solar cells. So when the shutter opens, the shutter is basically the cover of the camera. It opens for a fraction of a second to capture the image as a pattern of electric charge, which can be stored as data on a memory card. Then this data can be processed to produce the final image on a screen or in print. This is the amazing process the camera goes through to record an image or a video. So what we're trying to basically understand here is that a convex lens is used in this camera to form a real image, which is then censored by a light-sensitive microchip containing millions of microscopic solar cells. So this captures the image as a pattern of electric charge and can be stored as data on a memory card. So here we are using the convex lens in the camera to form images. The second example is the human eye. So like a camera, a human eye also uses a convex lens system to form a small inverted image at the back. So you can see here, the rays enter the eye and pass through the convex lens and converge at the retina. They converge at the retina to form the image on the retina, which is upside down and is a real image, a small upside down real image. So the light is mainly converged by the cornea and the watery liquid behind it. So the cornea is a thin layer covering the iris and the pupil of the eye. After the cornea, we have a watery liquid. So there is a watery liquid behind the cornea at this part, this empty part. So this watery liquid and the cornea helps to converge the light. So when they converge the light, they make it pass through the lens. This lens, which is flexible, is used to make focusing adjustments. Its shape is changed by a ring of muscles you can see here. These are the two muscles. So the image is formed on the retina, which contains over 100 million light-sensitive cells. These are the light-sensitive cells. So signals from these cells are sent to the brain along the optic nerve here. So that is how the brain sees an image. So this image passes through the cornea and gets converged by the lens. The lens makes focusing adjustments to focus on the image, and the image is formed on the retina at the back of the eye. Now the retina contains 100 million light-sensitive cells, and signals from these cells are sent to the brain along the optic nerve. So the image is then made up in the brain. So that is how the image is made up in the brain. So this was the human eye. It was such an amazing thing to understand how our eyes can see and form images in our brain. Okay, so now that we've understood the two main uses of convex lens, the two examples which uses convex lens, the camera and the human eye, we're now going to move ahead onto looking at how we can correct eye defects in vision using these lenses. By eye defects we mean like short-sighted people and long-sighted people. We're going to look at these. So with many people, changes in the shape of the eye are not enough to produce sharp focusing on the retina. So what happens is that the changes in the shape of the eye are not enough to produce sharp focusing, so the image appears to be blurred. So to overcome this problem, spectacles or contact lenses have to be worn. So we have two types of sight, the long sight and the short sight. In a long-sighted eye, the lens cannot be made thick enough for looking at close objects. This, as you can see here, is a long sight. So the rays are not bent inwards enough. So when they reach the retina, they still have not met. Here you can see in this diagram a long-sighted eye. So the lens cannot be made thick enough, so the rays are not bent inwards enough. So when they reach the retina, they still have not met, and that is why a blur image forms. So to correct this fault, a convex lens is placed in front of the eye. Here you can see a convex lens. This convex lens helps to bend the rays inwards enough so that the rays meet at the retina and the image which is formed is clear. Okay, this was the long-sighted eye, and we use a convex lens to correct the long sight. Now, in a short-sighted eye, the lens cannot be made thin enough for looking at distant objects, and so the rays are bent inwards too much. They converge before they reach the retina. Here you can see this. The retina is over here. It's supposed to converge at this point. Instead, it converges before, and the image which is formed is again blurred. So to correct this fault, a concave lens is placed in front of the eye. The concave lens helps the rays to converge at the retina. So the image which is formed is again clear and sharp. So in a short-sighted eye, a concave lens is used, whereas in a long-sighted eye, a convex lens is used. A long-sighted eye is when the lens cannot be made thick enough for looking at close objects, so the rays are not bent inwards enough. So when they reach the retina, they still have not met. This is called, and this type of sight is called the long sight, and we use a convex lens to correct this fault. Whereas in a short sight, the lens cannot be made thin enough for looking at distant objects. So the rays are bent inwards too much and they converge before they reach the retina. So a short-sighted eye is when we cannot look at distant objects, whereas a long-sighted eye is when we cannot look at close objects. These eye defects come over the years. Eye defects come over the years as people grow older. The changes in the muscles in the eye are not enough to produce sharp focusing on the retina. Sometimes people are born with eye defects, so they are supposed to wear glasses from their childhood. So this is how we use lenses to correct the long sight and the short sight. I hope you have understood this. This was all about lenses. How we correct eye defects in vision with lenses. The examples of lenses like the human eye and the camera. The two types of lenses, the concave lenses and the convex lenses. Images formed by the concave lenses and images formed by the convex lenses. The real and virtual images. The standard rays to draw the diagram. Converging lens, diverging lens. The convex lens converges rays, whereas the concave lens diverges rays. So I hope you have understood lenses. So now that we've understood lenses and all of the different things about lenses, we're going to move ahead onto another different topic of this chapter, and the last but not the least topic of this chapter, the electromagnetic waves. So in this topic, we're going to look at light as well as the electromagnetic spectrum. So let's start without further ado. It's a very simple topic. It's not going to be very difficult. So, light waves belong to a whole family of electromagnetic waves. And these electromagnetic waves have several features in common. For example, firstly, electromagnetic waves including light rays can travel through a vacuum. Secondly, they can travel through a vacuum at a speed of about 300,000 kilometers per second. So this is usually called the speed of light, although it is the speed of all the electromagnetic waves. Thirdly, these waves are transverse waves. We have read this before in the waves and sounds chapter. These are the features that all of the electromagnetic waves have in common. So their oscillations are at right angles to the direction of travel. It is the electric and magnetic fields that are oscillating, not material. Okay, lastly, they transfer energy, all the electromagnetic waves, including light. Of course, light is included in the electromagnetic waves. So a source loses energy when it radiates electromagnetic waves, and a material gains energy when it absorbs them. So they transfer energy. They are transverse waves, they transfer energy, they travel through a vacuum, and they can travel through a vacuum at a speed of about 300,000 kilometers per second. So these were the features the electromagnetic waves have in common. Now let's look at the electromagnetic spectrum. So the full range of electromagnetic waves is called the electromagnetic spectrum. The range of wavelengths is huge. Okay, so at one end are the longest radio waves with wavelengths of several kilometers, and at the other end there are the shortest gamma rays with wavelengths of less than 1/1000th of a millimeter. This is the electromagnetic spectrum. Gamma rays have a short wavelength and radio waves have a long wavelength. So this visible light spectrum contains all the colors from the rainbow. Roy G. Biv. This is a short form, we can memorize all the colors. Roy stands for red, orange and yellow. G is for green, and Biv, B-I-V, is going to be blue, indigo and violet. So this is the order of the colors. And because red starts from here, we're going to read the electromagnetic spectrum from this side, from the radio wave side, rather than the gamma ray side, because we read the visible light spectrum as Roy G. Biv. We read it from the red first. Even though we can read it from the violet, it's just that to memorize the electromagnetic spectrum, we should start from this side. So the first waves are going to be radio waves. Then we have the microwaves and the infrared rays. After this we have the Roy G. Biv. We call these the infrared radiation because they are on the red side of the electromagnetic spectrum. After this we have the ultraviolet rays, which are on the violet side of the light spectrum. Then we have the X-rays, and lastly the gamma rays. So this is the electromagnetic spectrum. Memorizing it can be very helpful. So here we have the spectrum of light. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Now, where do all the electromagnetic waves come from? This is a question which has a very simple answer. All matter is made of atoms, and atoms are themselves made up of a central nucleus with tiny particles called electrons orbiting around it. The nucleus is made up of protons and neutrons. Anyways, the nucleus and the electrons are electrically charged. So sometimes electrons can escape from their atoms. For example, when an electric current passes through a wire, the current is a flow of free electrons. Mostly metals have free electrons because they're good conductors. So this is how electromagnetic waves are formed, when electrons escape from their atoms. So now let's go through all of these electromagnetic waves one by one, starting with radio waves, the first wave of the electromagnetic spectrum. These are the rays which have the longest wavelength and the lowest frequency. So radio waves are used to broadcast radio and television signals. These are sent out from an aerial a few kilometers away. An aerial is a transmitter basically. So these waves are sent out from an aerial, a transmitter, a few kilometers away to be captured by an aerial on the roof of a house. Do you know that stars are natural emitters of radio waves? Radio waves can be detected by radio telescopes. However, radio waves can be produced artificially by making a current oscillate in a transmitting aerial. So, in a simple radio system, a microphone controls the current to the aerial so that the radio waves pulsate. In the radio receiver, the incoming pulsations control a loudspeaker so that it produces a copy of the original sound. So this is how a radio works. Okay, so this was the radio waves. Hope you understood them. After the radio waves, we have the microwaves. Microwaves are used in satellite television broadcasting because microwaves pass easily through the Earth's atmosphere. The second point is that microwaves are also used to transmit mobile phone signals between masts. After microwaves, we have infrared radiation. So infrared radiation has a lot of uses. The first use of these rays are in remote controls for devices. Infrared radiation, microwaves, radio waves, they all are invisible to the naked eye, except for the light. Light is the only part of the electromagnetic waves which is visible to the naked eye, whereas all of the other rays are not visible. Of course, because they transfer heat, they can be felt. So thermal radiation is infrared radiation, because grills, toasters and electric stoves also use infrared radiation because it is thermal energy on the move. So anything that is heated up, and when we go near the object which is heated up, we can feel the infrared radiation. Security alarms send out beams of infrared rays and detect changes in the reflected radiation. These may indicate the presence of an intruder. And of course, infrared rays cannot be seen. So yes, this is how infrared rays are used for security as well. So after infrared, we have the visible light spectrum, and after the visible light spectrum, we have the ultraviolet radiation. So, ultraviolet radiation is used to sterilize medical equipment as it destroys microorganisms. Remember, ultraviolet radiation is very damaging. Ultraviolet radiation can damage living cells, and for this reason, it is hazardous to use sunbeds, which are designed for tanning for fair skin. Ultraviolet radiation also comes from the sun. That is why we use sunscreens and sun protection, so that the rays cannot harm our living cells. Don't harm us, because ultraviolet radiation can damage living cells and can be a cause for skin cancer. They are very hazardous. Fluorescent lights produce ultraviolet radiation by passing an electric current through mercury vapor. So these were the uses of ultraviolet radiation. Okay, after the ultraviolet radiation, we have X-rays. And X-rays are used in security scanners at airports. X-rays are also used to detect cracks in metal objects and in hospitals to see inside patients without having to perform surgery. X-rays can also be hazardous to health if we are exposed to them quite frequently. But of course, if you're having an X-ray once in a year, once in 2 years, if you have an X-ray once in 2 years, then it's not as dangerous as it is for people who are around X-rays a lot. So that is why they wear protective suits to keep them from the X-rays. X-rays are used to kill cancerous cells. So yes, X-rays can also damage living cells, but because they do so, we use these X-rays to damage cancerous cells. Even though a great amount of collateral damage occurs because of this, because when we are killing cancerous cells, the cancer-free cells also get killed. But still, many people have survived from cancer because of this. Lastly, we have gamma rays. And gamma rays have similar use to X-rays in medicine and engineering. Gamma rays again can be used to detect cracks in metal objects. They are used in security scanners at airports and also used in hospitals to see, and are also used to kill cancerous cells. So these were the electromagnetic ray waves. An important thing to note is that the speed of all electromagnetic waves is the speed of light, which is 300,000 meter per second, or 300,000 kilometers per second. Also, all electromagnetic waves are transverse waves. These are the 2 points that we have to remember. So, I hope you have understood these electromagnetic waves. So the electromagnetic spectrum and the electromagnetic waves are very simple, as you can see. So this was all for today's chapter, Rays and Waves. This was our 7th chapter and we have completed it successfully. And you can see it was a very big chapter, but also a very interesting and diverse chapter. In this chapter, we learned about light, the wavelength and color of light, the reflection of light, the laws of reflection, how we can find an image position in a mirror, refraction of light, the refractive index of different materials, the different equations we learned in this chapter as well, the refractive index equations, total internal reflection, reflecting prisms, we also understood prisms, the dispersion of light, and we also understood Snell's law, sine I divided by sine R is equal to n. We understood the critical angle and total internal reflection, and after this we understood lenses, the two different types of lenses, the convex lenses and concave lenses, and the images produced by these lenses, real images and virtual images, and so much more. It was so interesting, wasn't it? And last but not the least, we understood electromagnetic waves and the electromagnetic spectrum, and this was very simple to understand. So this was all about rays and waves. So thank you for watching this video, and our next 8th chapter is going to be electricity, and that's going to be very interesting too. So thanks again for watching this video, and I'll see you in the next video.